Hello, student. Today I discuss about vector space. So you are looking on the screen. What is a vector space? This is a three-dimensional figure. Here, this is x-axis, this is y-axis, this is z-axis. So the in the Cartesian plan, two-dimension or three-dimension, to represent a vector is a very important thing. First, we know what is a vector field. I have already discussed about ring, field, groups, what is a billion group, what is commutative group, what is a field. Now, what is a vector field? So, here you can look that what is a vector field. So, vector field is in another term, a linear space, vector space or a linear space. So, if what is called a vector space? Here is the definition. We know that what is a field. Field can be real numbers also generate a field, and complex number also generate a field. So um, vector space is defined as the collection of the vectors which may be added together and multiplied by numbers called scalars, which are taken from the field, and scalars are often taken to be real numbers. But there are also we can be it is not necessary. They can be also a complex number. If the field is formed from real numbers, then the vector space called real vector space. And if the vectors, if the scalars are taken from complex numbers, this is called complex vector space. Now, this is a two-dimensional figure. There are two vectors v and w. So and v plus w is there uh, uh, is the it is presented through a parallelogram, and v and w are the adjacent side, and v plus w is the so to understand the vector space is very important to know what is the behavior of vectors. So uh, this is the resultant of the two vectors. You already know from vector algebra that if two vectors through parallelogram, if two vectors are represented by two adjacent sides of parallelogram, then the diagonal represents the resultant of the two vectors. So v plus w is that is through vectors. V plus w is the is in vector form represents the resultant of the two vectors. Now let's see this how. take first take a triangle law of vector. If there are three sides of a triangle, so this is vector A, vector A, and this is vector B. Both are in same direction, anti-clockwise direction. If we take a reverse direction or a clockwise direction, then we will get the resultant vector, which is equal to the resultant vector is equal to the sum of the two vectors. Sum represents the direction and the magnitude of the vectors, but not properly the magnitude of the resultant. This is the vector notation to represent. It does not mean that through this equation or this representation you can calculate the resultant. We know from vector algebra what is the how the value of the resultant can be obtained, and how the um, angle of the resultant can be obtained with respect to the vector A or with respect to the B. I have already launched many videos vector algebra. You can look this to understand. Or a parallelogram law. If we take, there are two adjacent sides can be represented by two vectors, A vector and B vector. B vector. So the diagonal is in the resultant vector. This is also B vector. This is parallel to B vector. This is B vector, and this is the resultant vector. So these are the very common uh, knowledge of vector algebra, and you know the rules of the vector algebra. How can the resultant can be obtained? So I am not giving this. I am just giving the representation of the resultant of the vectors. This is A vector and this is B vector. So now how we can define a vector space? You already know what is a field already. Through this knowledge, we will define what is a vector space. So what is a vector space? Vector space is a over a field, any field, if it can be real or complex. It is a mapping from V cross V to the field F. B is the collection of the vectors and F is the collection of scalars, which is a field. So the mapping from V cross V to the field F is denoted the operation of a vector space, or it forms a vector space. So some properties need to be fulfilled. First, associativity, then commutative, then identity element. There must exist a zero vector. Uh, there must exist a zero vector uh, for which we will get the same element. So there must be identity element which is zero vector. Inverse element must exist because the binary composition is addition. So zero must be the identity element and inverse element must exist. The negative of every element is the inverse element. Compatibility. Compatibility is the A scalar A and B belongs to the field F and B belongs to the vector. Then if we take the second scalar with the operating with the vector, and then the first scalar operating with the second, and then we will get if we multiply the both scalars and operating with the vector, we'll get the same result. And there must be identity element in scalar multiplication. Scalar multiplication is a field. We know that field is a abelian group with respect to the operation multiplication. So there must be identity element 1. So 1 is equal to b. The multiplicative identity 1 is in f, and distributive, that a and addition of two vectors a plus b, there will be a distribution eu plus ab, and distributive of scalar multiplication is the field addition a plus bb equal to ab plus bb. So these are the axioms must necessary should be fulfilled to be a vector space. Now I discuss more things about this. You have to know, to understand basis and dimension, you have to know what is linearly independent or what is linearly dependent set of vectors. So let's see linearly dependent and linearly independent. First we know what is linearly dependent. Linearly dependent set of vectors are that those if with scalars not all zero, like lambda 1 v1, v1 is the vector, lambda 2 v2, dot 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 up to n vectors and n scalars, will get the addition or summation equal to 0. But to get the result 0 or 0 vector, if all the lambda 1, lambda 2, lambda i's not equal to 0, not all equal to 0, not all, then we said that the set of vectors are linearly dependent. And if it happens that all this formula, this representation will get by all lambda is equal to 0. All lambda is equal to 0, if then only uh, then only if we will get this result, then we can say that the set of the vectors v1 v2 dot dot vn all are linearly independent. So it is clear, I think, means the vector not dependent on each other, they are linearly independent. Its meaning, and if the vectors are dependent through a equation, then they are linearly dependent. So we also now we also know about what is a standard basis for Cartesian plan 2. The standard basis is Cartesian plan 2. Standard basis is 1 0 and 0 1. The two bases. These are called standard basis. because every and these um, basis vectors are also linearly independent. You can very easily verify through this putting. I'm not going to prove this. You can take into scalars. You can very easily prove that these are linearly independent. By any equation, you cannot make them dependent. So they are linearly independent. So these are not given by E1 and E2. These are the these are the linear independent vectors, and every element in uh, in the Cartesian plan of two dimension can be represented by this basis vector. Like take a point 25, you can very easily represent it through this um, basis vectors 2 e1 5 e2 very easily. So that's why any vector can be represented by these basis vectors. So that's why they are called basis of the uh, two Cartesian plan two dimensional. Any point can be represented by these two basis vectors, and the two basis vector is span whole of the two dimensional plan. For three dimensional, what will be? For three dimensional, u1 will be 100. It will be 0, 1, 0. These are also independent. This also you can verify. It will be 0, 0, 1. So in any point in the three dimensional can be represented by these three vectors. So these three vectors is for all of the plot, and that's why these are called the basis vectors of the three dimensional plot. And they are also independent. So you can very easily verify this. So this is the standard basis. These are called standard basis. You can generate other bases also which are not standard, and just the condition of to be a basis is that they must be linearly independent. The basic need, they must be the linearly independent, the basis vector. They must span whole of the plan. Span means that any other vector can be represented by the basis vectors. So this is the definition of the basis. And what is the dimension? Dimension is that the number of elements or independent vector elements in the basis is called dimension. Means that for the Cartesian plan 3, the standard basis we get 3. So the dimension of the three-dimensional space is 3, and the dimension of two-dimensional space is 2. So this is the dimension. Eigenvalue and eigenvector already discussed in matrix. This is not different. These are the same which I have discussed. How to calculate eigenvalues or eigenvectors. So look the other videos of released by me, and you can easily understand what is eigenvalues and eigenvectors. This is important. Norm vector space and uh, inner product space. So I first discuss inner product space. Inner product space is another term called Hilbert space. Uh, Inner product is a vector space V for the field. It is another type of vector space with a extra operation inner product. So uh, how the operation operates, there are three conditions axioms must be fulfilled. First, conjugate, that uh, every vector in the inner product must be conjugate with must be also conjugate. That means its conjugacy must be symmetric. Means if xy is the inner product vector, then its conjugate vector uh, is yx, and the bar shows that conjugacy must be equal. And linearity is that if a is a scalar multiplied with the inner product exy, then we'll get the scalar out of the inner product. Very important. And this linearity addition of to any vectors and taking the inner product with the vector j, then we'll get um, two different inner products a z y z with the order followed. Means x kept is in the first position, y kept in the first position. Positive definite you know already from matrix, that positivity is that mm, for all the vectors must be through the operation inner product must be greater than 0. Then these are called positive. Three axioms must be necessary for being a for being a inner product space. So this is a very important. Now I wish to introduce more thing. Non-vector space. Non-vector space is that is also a very important vector space. The difference between non-vector space and inner product space is that uh, norm the operation norm is defined on the vector space. Vector space, then the vector space is called non-vector space. If inner product is defined on the vector space, then that this is called the inner product space. So they are the basic difference. Here, a norm is defined also on the vector space, and some properties must be fulfilled. Norm, you know that what is a norm. I am giving it in another format. This norm is very important. What is a norm? Norm is another kind of distance. Norm is actually another kind of distance. Norm is given by in this way. This is the uh, mm, notation of the norm of any norm. So just show norm of any vector. Norm of any vector. So uh, take any vector and a collection of vectors. This is V, and Ax belongs to V. X is a in this collection. Then norm is defined that if X is, I am taking let AI plus BJ J plus yes, this is CK. Then norm is defined in this way. Norm is root over A square plus B square plus C square. So you can very easily look that this must be always greater than equal to greater than 0, and it is norm if norm is equal to 0, norm of x equal to 0 if and only if x is a 0 vector. Otherwise it can never be 0 if and only if x is a 0 vector. And norms, other properties of norm is that any scalar if multiplied with this norm of ax, a is a scalar from any field, then a comes out from the operation of norm. This is another property of norm. This equals one property. This is the second property, and third is the triangular property. What is the triangular property? Triangular property is that norm of any two vectors x plus y must be less than equal to norm of x. How norm can be depicted in a figure through a figure? I'm giving a figure. You can very easily understand through this figure. Norm. Norm is a one kind of distance or modulus of any vector, you can say. So I'm giving two-dimensional figure to make it understand. Two-dimensional figure. This is x-axis. This is y-axis. So if you take this is a vector a small x, and this is a vector y. So modul modulus of the vector ax is called norm. Norm of ax is the vector dot product of the two vectors. You know that two operations of dot product and scalar product and vector product, cross product. So norm of vector is the just a dot product. So it shows the you can say the dot product of the vector. So it must be equal to of its components of through x-axis and through y-axis. So if we'll take x is if we draw it in three-dimensional figure, it is also z. So norm of x you can very easily calculate through this equation, and norm of y also can be calculated very easily through this equation. This will be the y dot What will be the resultant triangular inequality? This is the triangular inequality that x plus y, this is y, so here is the in this diagram, if we take x and y as a position vector, then it cannot be calculated. We erase this. Actually, this is not a position vector x and y. So it must be in this way. If this is x vector and this is y vector, then the resultant is the xy vector. So you can easily calculate the norms of this. The norm of x plus y, norm of x plus what will be? Norm of x plus y will be just x plus y, addition of the two vectors, dot addition of the same vector, addition of same two vectors, x plus y, x plus y. So these are the properties of a norm. If these three properties is happens, then norm generates a space on the on the vectors. So we know norm is one kind of length, you can say. So these three properties must be defined on any vector space through a norm. Then the vector space is called non-vector space. Here one thing I have done mistake. There will be modulus. Is very important. You cannot ignore this. There must be a modulus of the vector because it can be a complex. If you will take the field complex, then A is the complex number. Then the mode of the modulus is a very big factor. And if it is a real number, then it does not matter. But if it is A is a scalar of a field can be one dimensional, two dimensional, three dimensional. Then a modulus is a very big factor. So it must be remembered. Now you have already known that what is a non-vector space and uh, uh, what is a non-vector space and what is a inner product space. So I have just giving the introduction of non-vector space and inner product space. Energy space is a very strong space. So I today will not discuss about it. After you engulf all these knowledges of phase spaces, then we will go the senior level of topics. Dirac space, Hilbert space, and their properties will be discussed later. So I am looking another properties of non-vector space. If there is These are the LP spaces. LP spaces is defined in this way. LP is spaces is that norms are defined on functions or mappings. So if the order of the norm is P, then this will be the norm on any function is defined by the integration of modulus of f of the function of order P, and their pth one by p pth number of root. So this is the mm, this is the norm defined on any function. So LP spaces are very important, and you have to remember how the norm is defined. Now, now vector spaces are more easy if you know the all the components of your norm, and if you have clear knowledge about what is a vector space, then you can very easily understand what is a non-vector space. So I am not getting more information to discuss in this topic. I am looking inner product space. There is more information and basic information actually need to know or to understand other properties or other theorems on based on these uh, species. So we have to very clearly know how the basic informations are. Very helpful request. I am just ignoring this for this video, and in another video the balance space and equilibrium space will be discussed. Other things too much. So up to this I am leaving now. Here are two theorems. You can look in this figure. Theorem I'm not proving today. And for polarization identity, another important. These two laws, theorem law and polarization identity, I will discuss in another video. So uh, for uh, for just today, I I'm leaving, and thanks for watching to all of you, and just study carefully, and I will in next video discuss the senior topics. So just mature yourself to make understand the senior topics. Thanks for watching, and thanks, and subscribe this channel to get all the videos at first in your handset. So must subscribe and must share with your friends. Thanks a lot.